Welcome back. Welcome to the online edition of CMIS468, where we're beginning Chapter 8 content today. And today's broadcast is brought to you by the letters K and C, as in Kansas City and King Crimson is your band from way back in the day that I want to introduce you to. It is highly unlikely that you have ever heard of the band King Crimson. If you have, you need to let me know immediately, because that would be way cool. It's a pretty obscure band. If you're into early 70s jazz fusion rock punk metal, then you know this is the band for you. They're a little inaccessible. King Crimson is an early progressive rock band formed in London in 1968. Hence, this is the 50th anniversary tour that my wife and I made a pilgrimage to Nashville, Tennessee, back in September to see the Crimson. One of my all-time favorite bands, and led by the magnificent Robert Fripp. Sadly, part of the reason I'm wearing a King Crimson shirt today is that one of their drummers, I say one of their drummers, they've had many, passed away, not due to coronavirus, but due to cancer. But sadly, he was very young at 59. Let's see. When I say one of their drummers, this was the lineup that we saw in Nashville with, I've never seen 3 separate drum kits used before. It was pretty amazing. I showed part of this in the other class, but I'm going to show you guys something a little different. This is off their 1982 album, Discipline, that has a very famous logo on the cover that they kind of took as their band logo. So what happened was, I didn't tell the other class this. When I went to the concert, I went to the merch table and I got a t-shirt, of course. But they were also, okay, I'm knocking everything over, selling, that was exciting, belt buckles. I don't know if you can see that, but it's the same logo as on my favorite album. So, I mean, I attached it to the belt myself, because back in the day, boys and girls, we used to wear big-ass belt buckles. I don't know why, we just did. So I got one, but the woman at the merch counter was a little snarky with me, and I'm like, let me get one of those belt buckles. And she says, and I quote, "Yeah, I figured these would do well in Nashville." Excuse me? Slow your roll. I think she just called me a hick. I didn't care. I bought it anyway. So here's a track from my favorite album called Thela Hun Ginjit. Yeah, that's a song called Thela Hun Ginjit, which means nothing. It's a made-up language. It doesn't mean anything at all. They just thought it sounded interesting. Thela Hun Ginjit. Anyway, sadly, that's enough about the Crimson for now. So let's talk about things that are maybe more on your mind. The exam is posted on Blackboard right now. I'm recording this on Wednesday the 25th. Maybe you've already taken it at this point, but you've got Wednesday, Thursday, Friday, a nice big window to take it in. It's on Blackboard. Scroll down on the left-hand side under the exams folder inside 468, and you'll see it there. The password is right there in the instructions. I do expect you to take it as if you were taking in class. I'm not proctoring you, but no notes, no textbook, no slides, no help, no internet, no nothing. So good luck. And of course, if you have internet problems or it blows up or the test freezes on you, don't panic. Just let me know and I'll fix it for you. You've got your next assignment coming up is April 1st. It's worth 20 points only because the assignment that it's replacing, the Wi-Fi site survey, was worth 20 points, but I'm too lazy to go back and redo all the math, so let's just leave an easy assignment worth 20 points. Man, Chapter 8 is where it all starts coming together. This is networking crap at this point. I have rearranged some things to kind of keep all the routing stuff together, all the IP addressing stuff together, kind of layer by layer, so that it makes more sense. I'm going to cover all the same material that's in the chapter, but slightly out of order. Things we need to talk about: addressing, subnet masks, the difference between a border and internal router, what a router does, how a router does what it does. It's pretty simple. It's pretty straightforward, but very test worthy. Okay, for the next exam. Exam number 3 will have this information on it. In part 2, next week at this point, we'll get into IP version 6 and some other topics. But for now, let's jump into where routing is in our 5-layer salad. We're going to start off by talking about layer 3, right in the sweet, chewy center. This is where all the sweetness is of the 5-layer stack. Layer 3 is about 2 big things, or 2 big topics we have to talk about in layer 3. One is routing, and the other is IP addressing. Routing and addressing, routing and addressing. These are the 2 big things. Where do they fit in the 5 layers? Well, we're right here in the middle at layer 3. So with IP addressing, we will get into some layer 4 stuff next time, but right now we're in these 2 layers. So what is layer 3 about? Routing and addressing. Now remember that every host has to have a network address. When I say a network address, I mean an IP address. Actually, every network card has a burned-in MAC address, the physical address, and then it also has that can't change unless you're running Linux. It can't change. In addition to that, that's at layer 2. At layer 3, we have an IP address that we only need for routing internet traffic. If you don't need to get out on the internet, you don't need an IP address. But every single host, and yes, just to be a little more precise, every single network card has to have a unique IP address. Because imagine you've got a server, you can put 2 network cards in it. These would be two different IP addresses. A better example would be a firewall. Has 2 network connections, an in and an out. These are, you can think of these literally as 2 network cards, each with a unique IP address. Same thing with a router that we're going to get into. Needs at least 2 IP addresses for the in and out. Remember that there's a difference between private IP address space and public IP address space. What that means is private IP addresses are used inside your own internal network, behind your firewall. Behind your firewall, you're using private IP addresses. Things like 192.168.111.1 or 10.1.1.1. Some legitimate, we'll talk about what that means, a legal private IP address space. Public IP address space is the public IP that's assigned by your ISP, be it Charter, Verizon, AT&T, whoever your ISP is, Comcast, whoever it is. And then the number of bits in an IP address in a version 4 IP address is what? No, I heard some of you say 48. That's a MAC address. It's 32 bits in an IP address. Are you going to get this question in a job interview? Yeah, I think you are going to get this question in a job interview. It is entirely possible that in any kind of network admin role or even operational role, possibly even help desk role, you're going to get rapid fire a lot of these questions. How many bits in an IP address? Google, when I was interviewing with them, asked me that, just one after another. How many bits in an IP address? What's this? What's that? What's a subnet mask? How does DNS work? How does DHCP work? Just one after another. Okay, so these are the big things to keep in mind. So routing and IP addressing are really interconnected, but let's start off talking about routers. On a switch, you know, that device, here's where, if we were in the classroom, I would point to the network rack and show you all the ports on a switch. It's easy to tell a switch because it's got 12, 24, 48 or more ports on it. We don't talk about ports on a router for a variety of reasons. We talk about interfaces, but there's still those little RJ45 connections on the router. But you just have an in and an out, maybe a console port. You've got maybe 3 RJ45 connections on a router, but let's call them interfaces for now. And physically, what I'm talking about are, you know, just the RJ45s on the back here. Next time we're in the classroom, I don't know when that's going to be. year far in the future, in the year 20 whatever, after the pandemic clears up, we can look at routers together. But there's just a couple of interfaces on the back. It's a lot simpler. You might also have some serial interfaces for your WAN connection, which are going to be a wider type of port. Routers, this one is like, call it 3 rack units in size. Routers come in all shapes and sizes, from your cute little, all-in-one multifunction device at home to small office routers that might also include like a wireless access point, to more typically dedicated boxes. What I mean by dedicated boxes, it's a box on the network that is only doing routing. It is only operating at layer 3. It's not doing anything else. It's not your firewall. It's not your switch. It's not your access point. It's not serving up DHCP. It's not doing anything else besides just routing. It does one thing and does one thing really well. Routers can get into this behemoth size where it's more of a multifunction device, right? Where you've got switch ports and a routing module, and you're connecting to multiple different types of networks and running lots of different protocols. This would be for a very complex environment. Or maybe you need something that has fiber optic ports on it as well. Sorry, interfaces. But routers come in all shapes and sizes. We've got a few in the network rack in our room. But if I can really simplify this for you, a router is that magical device that allows your network to talk to somebody else's network. So here's your private network, your LAN. If you want to connect a WAN of any sort, be it the internet, be it a private leased line to another location that you're paying an exorbitant amount of money for, anything in the cloud, you need a router to connect the two networks. And it's doing a variety of things, but every router has an outside and an inside, a public and a private, an external and an internal, a WAN and a LAN. Depending on the manufacturer, it's going to be called different things, but there are 2 sides at a minimum to every router. Now, technically, you could have a third interface, third, fourth, fifth interface to connect to a bunch of different networks. Again, that's for a very complex environment, but it is possible. Routers are pretty darn smart. So the type of router that you're going to have on the edge of your network, if you want to think of this as your perimeter or border, same thing, the router that directly connects to your ISP, we could just as easily have drawn a cloud shape here. In fact, I would have preferred that. But your border router is a thing that's right next to that connects you to the cloud. There are other types of routers that you can have inside your network called internal routers. And you might use internal routers for a variety of reasons. Limiting broadcast traffic is a more technical one, but just to kind of isolate traffic onto different segments. It is a pretty good way to add another layer of security by partitioning off the network into different segments, if you will, by having like a router in each building so that it is its own network. And then your LAN is actually a collection of networks. You might need internal routers if you're connecting to a network that uses a different protocol. So back in the day at Corning, the R&D department used all Macs and they used AppleTalk as their protocol, not TCP/IP. And so we needed a router to interface between those two networks. Or if you have a network that uses a different range of IP addresses, say you're using a 10-net range and somebody else is using a 172 range. We'll talk about these different private address ranges. If you want to connect 2 different ranges of IP addresses, you need an internal router to do that wizardry. This might be very common in a situation where, say, this is my company, but I acquire a new little company and they are using a different IP address scheme than I am. I can just drop in an internal router to connect us to them and problem solved. Okay, remember at layer 3, two big things, routing and IP addressing. So at layer 2, where switches live, Ethernet uses a switching table. We don't call it a switching table. We call it the the spanning tree is the switching table. But just to picture, port, MAC address, port, MAC address. Similarly, a routing table is interface, IP address, interface, IP address. How does a router route? A router routes messages by using a routing table, and all that's in the routing table are IP addresses. And when I say that it's tattoo worthy, there's certain ideas in this class that are just so important. I'd be okay with you getting them tattooed somewhere on your body. The layers is the number one concept. But this idea of how do routers route, they route by using a routing table, is also tattoo worthy. I don't know why you'd get a damn neck tattoo like this, but hey, people do weirder things. So switching and routing are somewhat related concepts in that both are making forwarding decisions. They're forwarding messages across a network. But switches, again, work at layer 2, routers work at layer 3. This is just an illustration of going through multiple routers through a network. And that there are multiple paths through a network, I think is the point of this particular graphic, that a message can come into router A. Maybe it takes this path through router C, router E to this host, but it has some other options of going through router B to router D to router E to the host. Or if there's some congestion on this line, maybe it goes to C, B, D, E. I don't know. There are a variety of options here, and routing gives you those options. Switching versus routing. So I said a switching table has MAC addresses, a routing table has IP addresses, and then each interface has a number. Now, if you're a Cisco bigot like I am, all Cisco devices don't start their interface numbering at 1. What do they start with? So interface 0 is the first interface, but that's just a proprietary thing for Cisco. Some others do it. And then what the next hop router is. So any router can only see what's directly connected to it on the other side, and it has no visibility about what's on the other side of the next hop router. If I can illustrate, this is where a whiteboard really helps. This router knows about router B is connected to interface 1 and router C is connected to interface 2. That's all it knows. And it knows either to send it here or send it here. And if you're wondering how does it know which one to use, part of it is that these routers are exchanging their routing table information. That's part of how it knows which interface to send something out. But router A has no knowledge of router D or router E. Okay, it just knows what's one hop away from it. So it's pretty decentralized in a very clever way. So a routing table is going to have a row number. It's going to have a range of IP addresses, to send out this interface. It also needs a subnet mask, which we're going to get into because that's a tricky concept. We can assign it a metric in terms of just we can give certain routes a different weight. Like if we want to push more traffic over this line because it's less expensive, or because it's faster, or because it's more secure. It might be a variety of reasons. Try this one first. It's a kind of a priority for, try this one. If this one doesn't work, maybe do this one. So there's a way to put a metric to give a different weight to different interfaces. We talked about the interface. It's the same thing as the port and the next hop router. This is where I would, in class, jump up and down, hopping from one router to another. I'm just knocking things over left and right here. That's what we call it. This is a hop. This is a hop. This is a hop. This is something you saw in traceroute in the very first assignment I gave you. Right? You went to the command line, you did a traceroute to this IP address, and it showed you all the intervening hops between you and your destination. So what does a routing table look like? Well, it's just text. It's pretty unglamorous. It's just an example of what one might look like. The key here, though, is that Routers work by looking up their forwarding decisions in a routing table. So routing is the process of getting a packet closer to its destination. I would call this a forwarding decision. The routing table I showed you an example of. How does it make a decision? This is going to be all over the next exam. 3 steps it has to go to. If we were in class, I would have you just chant this with me in class. Step 1, find all the rows that match, where it could go out interface 1, 2, 3, which ones match. Find the best one. What does best mean? Well, it might be based on the metric. It might be based on, I can say, as the network administrator, I can define what best is. There are different algorithms for this. And then after I determine the best one, so I look all the possible matches, all the alternatives, all the alternate routes, to find the best one, and 3, send it out that interface. That's routing. That's routing in a nutshell. So just to belabor the point, find all the row matches. I might try to trip you up on an exam, and not just me, but on any certification exam, and test out Network Plus, Cisco, CCNA, any network certification is going to try to trip you up on this thing. Step 1, find the first available match, or find the fastest match, or find the best match. That's not the first step. The first step is finding all the matches, and then you make a determination what the best one is. What's best? It depends on the protocol you're running on your router. We will get into routing protocols later, I think in the chapter on WAN, so let's not get too complicated at this point. Yeah, best match, and then send it out. Now, let's talk about a problem that a student brought up with me. This is several years ago. I first started teaching telecom, and it said, Mr. Jacks, this is before I got a doctorate, and I was teaching part-time at a local college. Mr. Jacks, you keep saying that it's all about the layers, and layer 3 uses IP addresses, and layer 2 uses MAC addresses, and switches use MAC addresses, and routers use IP addresses. So how do they talk to each other? I said, I beg your pardon? Yeah, well, there are different layers, right? So how do they communicate? If routers are using IP addresses and switches are using MAC addresses, and we know that traffic has to go from the router to the switch to the host because everything's plugged into a switch, right? Isn't that what you said? That's what I said. So how do they talk to each other? How do they see each other? How do they pass messages from the router to the switch? And it caught me flat-footed for a moment, like, dear God, how does that work? Because I forgot about one of the other protocols in the TCP/IP stack, which is ARP. The Address Resolution Protocol simply resolves an IP address to a MAC address, and then reverse ARP, RARP, does the reverse. So the router doesn't know anything about MAC addresses. It has to learn about MAC addresses through the ARP protocol, which is what translates IP to MAC. Might be a test question in there. Yeah. Just sidebar, when we get into IPv6 later on, ARP is going away for some really freaky reasons, just to whet your appetite for more. But in IPv4 land, ARP is the secret sauce that connects layer 3 and layer 2 addresses. Well, we need to talk more about addresses now, so we're going to leave the world of hardware and routing and routers for now and switch over to the other topic in layer 3, which is IP addresses, which on the public side are given to you by your ISP or some registered number provider. Aaron.net is who assigns them. In fact, that's the only way to get them with IPv6. But Aaron.net is who assigns them to the ISP, who then assigns them to you. Each organization can chop up its address space, its IP address space into logical subnets. Now, there are a variety of reasons why you chop things up into multiple networks. And again, I would in class kind of launch into a discussion with you guys about what are the business reasons why we might subdivide a network. How do businesses organize themselves? So some standard ways are by location, by department, by product. When I say by product, Corning had an entire division for hardware and an entire division for cabling, an entire division for other glass products. So we want to divide our network, chop it up into different logical subunits that make sense for our business. And then we kind of take that business logic and apply it to our network decisions. And then within each subnet, every host has to have an IP address, as we keep saying. In this graphic, the textbook is just showing you an example of an IP address, what an IP address looks like. And in order to point out that there are three, even though there are 4 octets here, we'll talk about what an octet is. There are 3 parts, there are 3 kind of pieces of information we need. There's a network part, a subnet part, and a host part. These 3 down here. Network part, think zip code. Subnet part, think your street. And then host part, think the number on your house. Is one way. So from the general to the more specific is one way of looking at it. So 3 parts, a network part, a subnet part, and a host part across 4 octets. Here's the problem. We have no idea which part of the address should belong to the network and which part belongs to the host. Just by looking at an address, you can't tell. There's not enough information here to tell you which part belongs to the network. Which means you have no idea how many you can use. What do I mean by how many you can use? Well, if we're using, like out of a 32-bit address, if we've got 8 bits for hosts, that means we can have, like the math we did in class before spring break, 254 unique devices. But maybe I have more than that, and so I need to use some more bits from this 3rd octet. Maybe I want to use all of them and have 16 bits for my host so that I can have more hosts. But just by looking at IP address, I have no way of knowing how many hosts I can have on the network. So this is the problem. The answer is, and so continuing my Homer theme, to use a mask, sometimes called a network mask. I call it a subnet mask. If you want to think of a mask as something that kind of blocks up or masks, a mask covers up part of your face. A subnet mask covers up part of the network to show you which part belongs to the network and which part belongs to the host. So in this case, if I want to allow, 8 bits for hosts, to have 254 things on the network, I would reserve this part for hosts, and the remaining part is for the network. This is a complicated topic, and because of that, I want to do a deeper dive in the next video next week, because we really need to wrap our heads around subnet masks and the difference between a subnet and a subnet mask, because this is a common source of confusion. For now, though, if I could just try to help you out by highlighting, these are 2 things here. A subnet is just a logical division of the network based on business logic. A subnet mask tells you which part of an IP address is reserved for the network. I can't change that. I can't reassign any of those numbers. And which part is assigned for hosts. I can assign those to any device I want because I'm the network administrator. So a subnet mask and a subnet is just the kind of thing I would put on flashcards. Don't worry about tattooing this on your body just yet, but put it on flashcards to make sure you're really good with those definitions before exam number 3. And before I let you go, how about some more King Crimson?